All right. Good morning, everyone. Welcome to the first briefing of the day for January 8th. My name is Tarini Konchady. I'm the AAS Media Fellow. AAS Press Officer Rick Feinberg is at the back of the room. He'll be monitoring the chat for the webcast. So before we get into it, I'm going to ask you to silence any devices that can make noise. And there will be 4 press releases going out as part of this briefing. They'll be in your inboxes by the end of the hour. All right, so if this is your first time here, the way this works is the speakers give their presentations in succession, and then we open it to the room for questions. And then we take questions from the chat. So you may think that the subject for this briefing is a little odd. But if you'll remember, the Nobel Prize for Physics this year was split between cosmology and exoplanets. So we figured we'd do the same for this briefing. All right, so our speakers for today, in order, and their presentations. First up, we have Warm Dark Matter Chills Out, Constraints on the Nature of Dark Matter with Quadruple-Image Gravitational Lenses, given by Daniel Gilman of the University of California, Los Angeles. Next, we have a precision measurement of the Hubble Constant from time-delayed gravitational lens systems, given by Geoff, Chih-Fan Chen of the University of California, Davis. Next up, First Light for NEID, I am pronouncing that correctly. An extreme precision Doppler spectrograph for exoplanets by Jason Wright of Penn State University. And last, we have Living with Goldilocks K-Dwarfs, Stellar Effects on Hosted Planets, given by Edward F. Guinan of Villanova University. And with that, I'll let our speakers take it away.
So is it on here, or how do I access my? All right, thank you. All right, hello everybody. My name is Daniel Gilman. I'm a PhD student at UCLA. One of our main collaborators, Anna Nirenberg, is here in the front row also, from JPL. And I guess in the next 10 minutes or so, I'd like to describe some work that we did a few months ago that taught us something we didn't know about dark matter. And so to set the stage a little bit, this is a pie chart that you might have seen before, some version of it, showing what the universe is made of, what we think it's made of. And you see that most of it's dark energy, and then of all the matter that there is, only about 1/5 of it exists in the form of normal matter. The rest of it is in the form of dark matter, and we don't know anything about it. We think it's a particle, so it's stuff, but it doesn't seem to interact with our portion of the universe at all, except gravitationally. And so as you can imagine, one of the main goals of cosmology is to figure out what the stuff is. And what we know about dark matter today comes from basically the largest scales in the universe. And so what I'm showing here is a very zoomed out simulation. And this is a map, a simulated map of the dark matter, if we could see it. And all that's going on here is just gravity acting over time. And you can see that it forms all these structures. And this reflects, the picture that we have, that dark matter provides a scaffolding on which other structures like galaxies form eventually. And if you look closer, there are these really bright, dense blobs, and the technical term for those blobs are halos. And in the modern picture, all galaxies live in halos. So we think that each one of these halos is going to host a galaxy. And if we zoom in to one of these halos, we see additional structure. These we call subhalos. And this reflects a generic prediction of particle dark matter, which is you should have structure on many different scales. In some models, and then I should say that's a galaxy for scale here. So a generic prediction of dark matter models is that you should have structure on many different scales. In cold dark matter, these things basically exist on all scales. So down to the mass of a planet, up to the mass of the largest structures in the universe. And again, this is a simulated map of the dark matter. If we could somehow see it, this is what it might look like. And in cold dark matter, the cold here is referring to the particle's speed. And so this description is basically saying that cold particles, they clump together very efficiently, and then they form lots of structure, which you can just see by looking at the image. There are other classes of theories. So the one I'll focus on is called warm dark matter. And in warm dark matter, this is an umbrella term. It refers to any class of theories where you just wipe out structure below a certain scale. And you can see in the right here that there's just many fewer small halos than in the cold case. And like in cold dark matter, warm here is referring to the particle speed. So lighter particles clump together less efficiency and they form fewer structures. And one thing that's striking is that, regardless of the theory is cold or warm, it predicts an abundance of these halos, and most of them are too small to host a galaxy or to retain their stars. And so they're completely invisible. And so we say that every galaxy, we think every galaxy is in a dark matter halo, but not every halo is going to host a galaxy. And so if we actually just look out around our galaxy and we try to count up the little galaxies that we see around us, we can think that they are like a proxy for where the halos are, if all galaxies live in a halo. And we can make maps like this. So this is just a little schematic showing our galaxy in the middle and then all the satellite galaxies, the little galaxies around us that we can see because their dark matter halos have stars in them. But it's really difficult to go from this picture on the left to then telling the difference between these two situations on the right. So most of these halos are completely dark. We can't see them. We can't infer their presence by counting galaxies. And so we need some other way to do this. And in general, the different dark matter theories start to make increasingly divergent predictions on smaller scales. And so the further down in mass we can go, the more we can say about what dark matter can be and what it can't be. So the way that we are going to do this is using something called strong gravitational lensing. And this effect essentially allows you to see dark matter halos or infer their presence even if they're completely invisible and contain no stars. So this image is showing an image of a strong lens taken by Hubble, I believe. And on the right, this is a schematic of what's going on. So on the far left, there's a quasar. Its light is emitted, it travels out through the universe, and then it encounters some massive foreground object like a galaxy and its associated dark matter. And then as the light passes, it's deflected by the gravity of this foreground galaxy and arrives at our telescope. And so when we look at these things in the sky, we see multiple images of the background object at different locations around the foreground massive lensing structure. And these little perturbations that you see in the wiggles in the line, those come from the dark matter structures that we can't detect otherwise. They have gravity, so they participate in the phenomenon of strong gravitational lensing. And so this is a direct means of probing dark matter structure in the universe and inferring the presence of these halos that we can't see. And so to just make sure we're all on the same page about what's going on, this is a zoomed-in picture of that particular lens. In the middle, that's a galaxy. There's nothing funny going on here. That's just a regular galaxy. And then these four bright things around it are four duplicate images of the single background quasar. And they're highly magnified and distorted due to the strong lensing by this foreground galaxy. And it turns out that the relative brightness of these images is extremely sensitive to very small dark matter halos, down to around 10,000 times less massive than the galaxy that's producing the four images in the first place. And so we can use these systems to go way down in mass, down to where halos are completely dark, and we can use it to effectively count tiny dark matter halos. And this is not something that you can do with just a backyard telescope. Hubble is essential for this purpose. The reason why it's so important is because you have to measure the brightness of these images in a particular wavelength or a particular color. And the reason we do that is because we know that this wavelength or color is going to be uncontaminated by something called microlensing. And so to do this, you can see this is from one of Anna Nirenberg's papers. You take a spectrum of each image, and then you measure the brightness in a particular emission line called O3, which is labeled there on the right. And so this is a very advanced technique that allows us to get high-fidelity data that we can use to count dark matter halos. And once we do the analysis, our strategy is basically to generate maps of dark matter and see which ones generate realizations of dark matter structure in the universe, lens them, and see which ones give us data that looks like what we observe. And so this is one example of a simulated dark matter map that actually matches the observables precisely. And so I've marked on the left where the images would appear on the simulated dark matter map. And then on the right, this is actually what we see. So the right is the lens we see. The left is one possibility for what could be there. And it's a relatively good, it's a plausible example because it fits the data that we see. And so, in the analysis that we did, we took 8 lenses. We generated millions of different possible dark matter structure realizations in them. And then we tried to figure out what kinds of models reproduce the data that we observe. And based on this, I mean, because we had these precise measurements and because the models that we used were so good, we were able to go down in mass below 10 to the 8 solar masses, which is kind of a threshold where we expect halos have no stars in them or very little stars in them. And we were able to say conclusively that the kind of model on the right can't be true. So dark matter must be cold or relatively cold, and very warm models that fail to produce lots of small halos can't be right. And to kind of bring this back to what we see, this kind of result is consistent with the picture that our galaxy and every galaxy in the space between them is full of these tiny dark matter halos that are completely invisible to us. And so although what we see on the right is just a couple satellites, we are probably, according to results like this, embedded in gigantic dark matter halos that host thousands of tiny subhalos that are completely invisible to us. So to wrap up, this was done with 8 lenses. Upcoming surveys are going to find hundreds of lenses, and so we're going to be able to push these kinds of results to new limits and probe different kinds of dark matter models. And I think I'll leave it there. Thank you.
Okay, hi everyone. My name is Geoff Chih-Fan Chen. I'm from the UC Davis. So I'm here to represent the Holy Cow collaboration to present our newest Hubble Constant measurement. So my colleague Anwar Shajib also in this room here. Yeah. So okay, so I'm going directly to what's the highlight here. So what we found. So basically, we have used a completely independent methodology. Just strong lensing is already introduced by Daniel Gilman. But we use that system to measure the Hubble constant. And our result agree with the local measurement by the traditional distance ladder methodology. Usually referred to the supernova team, the Wright et al. And also the consequences is that the tension is very well likely real between the expansion rate of the universe and what's the prediction? What's the prediction from the standard cosmological model? Okay, so let me back a little bit, introduce what's the Hubble constant. So the universe has been expanding since the Big Bang, and the Hubble constant defines the current expansion rate of the universe. So it's the expansion rate now. So when we look at the sky, so all the galaxies in the skies, if we found that the galaxy is farther away, we will find it is moving faster away from us. So the ratio between the velocity, recession velocity and the distance from the galaxy to us, the ratio that defines the Hubble constant. Okay, so the Hubble tension is basically the two kind of measurement mismatch each other. And there are traditionally two ways to measure the Hubble constant. First is from the cosmic microwave background. So cosmic microwave background is from the very early universe. And then if we want to know what's the Hubble constant now, the expansion rate of the universe, we can assuming a flat lambda CDM model. This is the standard cosmological model that we know. And assuming the standard cosmological model, we can extrapolate what's the data from the very early universe and to now, to date. And then the Planck team derived the Hubble constant based on the flat lambda CDM model. It's a 67.4 plus minus 0.5. So this is a very precise measurement. But this measurement have a lot of caveat. So first, this standard cosmological model has a lot of assumptions. First, the universe is flat. So it means that when the light travels through the space, they will go straight line, it's not bended. And the second is like the dark energy does not evolve with time. So usually if we have the particle inside a volume, if the volume becomes bigger and bigger, then the density of this kind of particle should drop, right? But you will find the standard cosmological model assuming that the dark energy, when the universe is expanding, the dark energy density does not evolve, so it stays constant. So this is a very strong assumption. And also the effective number of neutrino species. So the neutrino species is from the standard model, from the particle physics. So based on this assumption, we got this number. But the interesting thing is from we can have a direct measurement from the supernova. Supernova is a standardizable candle. So this standardizable candle can help us if we can calibrate the luminosity of this object. If we see the object is less bright, and then we know that this object is farther away from us. So now we can, based on this object, the brightness of this object, we can know what's the distance. And then we can know, using the redshift, we know what's the recession velocity, so how fast they're moving away from us. So we can use the supernova to determine what's the Hubble constant. And now the result got the 4.4 sigma. So this is a well-known Hubble tension. And before, so whether this is require new physics, this is so very importantly, extraordinary claims require extraordinary evidence. So we really need to carefully check whether the measurement we did, does that measurement has a systematic we do not consider. So systematic means that we do not, when we do an analysis, there's a hidden something that we don't know but affect our result. So there is another team called the Carnegie Chicago Hubble program led by the Wendy Freeman. They found that they're using different methods to calibrate the supernova using independent data. And they found that the Hubble constant just right between the CMB, the Shields team, and the CMB team. So we really need to have the independent methodology to check whether there's a systematics. So the independent methodology, so why the gravitational lensing can play the role here. So gravitational lensing is not it's not like a supernova. They really need to calibrate the brightness. So it's just the gravitational lensing, just the light going through the massive star, massive object, and then you will bend it the light. And the gravitational lens quasar is a very unique object. So this kind of object is if their background source is a variable star, variable object, variable quasars, and when the light passing through the foreground galaxy, because the trajectory is different, so when they emit the light will arrive our Earth at different times. So this is a time called the time delay. So this time delay will help us to determine the overall size of this system. So you can see the video there, flipping between multiple images. And you can see the nearby galaxy around this object will also affect our determination of the Hubble constant. Okay, so the advantage of this methodology, we call it time delay cosmography, is that the simple geometry and well-tested physics, just simple GR, and then one-step physical measurement of a cosmological distance. So one step means that we do not require complicated calibration process. And you can see here, this is the, here. So you can see the dot here, this is represent the different imaging. And here you can see go up, brightness become brighter, and then the second go up, and third go up, and fourth go up. So by using this kind of monitoring, long-term monitoring, we can obtain what's the time delay between multiple imagings. And the second thing is that we need to know what's the mass distribution of the lensing galaxy. We use the very extended imaging. This is imaging from the RSA 1131 is one of the system. And you can see the extended imaging here actually is come from the background host galaxy. So this is the structure from the host galaxy. And every pixel in here, the thousands, tens of thousands of pixels here can help us to put very tight constraint on the mass distribution of the lensing galaxy. And then we need to study what's the environment of this system. So by looking at what's the galaxy surrounding by this system, and then we can compare what's from the simulation, we can compare whether this system is embedded inside the over-density region or under-density region. So that will also one of the very important rule when determining the Hubble constant. So by combining the three information, the time delay here, the mass distribution, and also the nearby galaxy information, and then we can determine the size. And the size will proportional to the 1 over h0, the Hubble constant. Okay, so this is the Holy Cow collaboration using the six lenses to determine the Hubble constant. Now we got 2.4% measurement of h0. And I want to emphasize here is that the blind analysis. So what do we mean blind? So it means that when we do the analysis, we hide the Hubble constant. So this is to avoid the confirmation bias, because usually people tend to reproduce something similar what people have been done before. So we hide the Hubble constant when we do the analysis. And when all the collaborators agree that we have already considered all the systematic, different mass model, different modeling technique, all the systematic we have considered, we unblind the result together and publish the result without any modification. So it means that possibly we can get the 50, very low value. We can get 80, very high value. We can also get the 67. But the result we got from the 6 lenses, we got exactly, I cannot say exactly, I should say consistent with the supernova measurement, 73.3 plus minus 1.8. Okay. So now combining with the directly, so because the SHOES program, so use the supernova, they also measure the Hubble constant. By combining these two measurements, because the two measurement is independent measurement, you can understand if we have a single value we want to measure, if we measure it more and more times, then we get more and more precise what the value it is. So when we combine the SHOES and Holy Cow, we got a very tight constraint, 73.8. So the precision is really high. So now it's reached 5.3 sigma. So what's the meaning of 5.3 sigma? It means that 1 out of 10 million chance that the true value is located at the Planck prediction, the lambda CDM prediction from the standard cosmological model. So it's very likely that the tension is real. Okay, so how do I name this 5.3 sigma? So let's introduce some terminology here. So larger than 2 sigma, we will say the curiosity, and larger than 3 sigma, we will say tension. And larger than 4 sigma, we will say problems. How about the larger than 5 sigma? Maybe it's a crisis. Okay, so maybe we should say that it's a Hubble crisis. Okay, so here I put my summary here. The time delay strong lensing achieved a 2.4% uncertainty h0 measurement with a 6 gravitationally lensed quasar. And the 2 independent and directly measurement yields consistent result, indicating a crisis in the modern cosmology. So only 0.00001% chance that the true value is located at the prediction from the lambda CDM model. And the new cosmological model may well be needed to resolve the tension. I put my colleague's name here, everyone also who contribute to this project here. Thanks, everyone.
Hi, everybody. I'm Jason Wright from Penn State University, and I'm speaking on behalf of the NEID instrument team. And today I'm going to tell you about first light on NEID, which is a precise Doppler spectrograph for finding exoplanets. And I'll explain what all those things mean very soon, but I have this very busy first slide because I wanted to emphasize how many different organizations have collaborated together to make this possible. It's too long a list to go down right now, but just it's been amazing to work with so many great people from so many places and see so much coordination to bring this to life. So NEID will be 3 times more precise than the previous generation of Doppler spectrographs. And the reason that's important is that higher precision means that you can find lower mass and therefore more Earth-like planets. So we're using the Doppler Wobble technique, and for scale, shown here, when the Earth orbits the sun, it induces a wobble in the sun's motion through space of 10 centimeters per second. And at the bottom, you see what it would look like if you were to observe the sun from another system and spread the light out with a spectrograph. You'd see the rainbow of light, but you would also see at very specific colors where the sun does not shine brightly because of chemical elements in its atmosphere, missing light, those gaps in the spectrum. And those gaps will move back and forth because of the Doppler effect. And so if we can detect those back and forth motions of a stellar spectrum, we can detect that the star is moving. And if we can detect them at the level of 10 centimeters per second, then in principle we can find things like Earth-mass planets around sun-like stars at temperatures where they could have liquid water. Now, the previous state of the art has been around 1 meter per second precision, which is 10 times worse than the signals that we are looking for. NEID is designed to have an instrumental stability 3 times better than this, so 30 centimeters per second. And I want to emphasize what an extraordinary technical achievement this is. If you want to measure a shift of 30 centimeters per second on our detectors, we're talking about 1/1000th of a pixel shift of those spectral lines going back and forth. If you want to find the sun moving at 10 centimeters a second, you're 1/3000th of a pixel. And for scale, a thousandth of a pixel is 15 silicon atoms. So this is an electron micrograph of a silicon substrate on a detector like we have or that you might have in the camera of your phone. Each of those dots is a silicon atom, and the 5 atoms in a row there, that's 10 centimeters a second shift. So this is extremely difficult to do. But we've been working on it for a long time, and I want to tell you that story. And that story, for me, starts 10 years ago with the publication of the 2010 Decadal Survey in Astronomy and Astrophysics. The National Research Council gave NASA and the NSF directions on where it should go with its major initiatives, and it recommended explicitly that NASA and NSF together should support an aggressive program of ground-based high-precision radial velocity surveys of nearby stars in order to validate and characterize exoplanet candidates. So the thinking was that NASA's missions like Kepler were going to detect lots of planets, and that ground-based NSF facilities would measure their masses using the Doppler technique. That same year, I was a brand new professor at Penn State University, and one of the very first things that I did was I helped organize a workshop on astronomy with exoplanets and precise radial velocities. And at that workshop, the world community, precise radial velocity community came together. The Decadal had just come out, and so we decided to write some recommendations to interpret that language and say what that meant to us and how we could help NASA and the NSF achieve those goals. And so our top recommendation was that the NSF and NASA initiate an open competitive program to develop precise radial velocity spectrographs in the US on the road to 10 centimeter per second precision. And so NASA and the NSF listened, and they put together NN Explore, which is a remarkable partnership for exoplanet discovery and characterization. And in 2014, they had that open call for proposals, and they invited instrument teams to propose a next-generation spectrograph that would go on the WIN 3.5-meter telescope at Kitt Peak National Observatory, which is run by the National Science Foundation. We were very pleased that the team, the very large team, all these institutions were on the team, but led it by Penn State, won the competition, and one of the key technological developments was to temperature stabilize the instrument to 1,000th of a degree, which has been very difficult, but we're there. And at the time, NEID would have an unprecedented instrumental stability, which would enable the most precise radial velocity measurements ever. So I keep saying NEID, let me explain where that comes from. The pronunciation is roughly NEID, rhymes with fluid. It means to see in the language of the Tohono O'odham. And we chose this name in recognition of the fact that Kitt Peak National Observatory in southern Arizona sits within the Tohono O'odham Nation. So fast forward 5 years, and this big $10 million spectrograph is complete in State College, Pennsylvania, weighs over a ton, and in comes a big forklift and picks it up to put it on the truck, and it's sitting there and bouncing up and down. It was very nerve-wracking. But everything went beautifully on both ends. It is now safely installed and not on a big lift like that at Kitt Peak. We now have first light. So let me explain how exciting first light is. First light is a key milestone in any instrument or telescope's development. It's the first time useful data is taken by the telescope or by the instrument. So we chose to observe 51 Pegasi for our first light observation because it was the first sun-like star found to have clear exoplanetary signal, and we did that in honor of last year's Nobel Prize in Physics for the discovery of exoplanets around 51 Pegasi. This is the first stellar spectrum from NEID that will be archived for posterity. We were very excited when it happened. Here we all are in the control room with our sparkling cider. There's no champagne allowed on the mountain. Some of us have our commissioning beards on. It was really just a great feeling after such a long journey to have taken a spectrum with that instrument. And immediately after this photograph, we got back to work because there's a lot of work to do. So I want to emphasize what's different about NEID. This isn't just another Doppler spectrograph, and that's because of NN Explorer, which is enabling really powerful new science. NASA is purchasing time on the WIN 3.5 meter at the National Observatory to be used under the National Science Foundation's Open Skies policy. Now that policy says anyone in the world can propose to use NEID for their science, and those proposals will be ranked competitively. So this isn't one university's private plaything. This is a national facility available to the entire world, and the best ideas around the world are what it's going to be pursuing in exoplanet discovery. And that's amazing and remarkable, and one of the things that I love about the NSF OIR Astronomy Lab. So here it is. I can show it to you now. This is NEID's official first light image. What you're looking at on the left is actually how the starlight lands on our CCD detector. We need extremely high spectral resolution. This is a very long spectrum. If I tried to show it to you all spread out like a prism would, like I did on the first slide, it would wrap around the room. And so the way that we do that on one detector is we stack it. So we disperse the light in both directions. If you were to read this in wavelength, you turn your head sideways and you would sort of read it like the lines on a page of a book or something. You'd go down one, start at the next one. If we zoom in really close, you can see there are actually two spectra here. The vertical lines you're seeing in green that are mostly solid are the spectrum of 51 Pegasi. The gaps in that are the spectral features whose positions we're trying to measure. And then the dots to the left are calibration light that we use to track the motion of the spectrograph during the night. So even though we're stable to 1,000th of a pixel, there are still drifts that occur that we need to correct for in real time. And so those dots tell us exactly what wavelength we are at with every pixel on the detector. And if I zoom in really close, you can actually see the pixelization in this image. Those are the actual pixels on the detector. So the precision of NEID is such that we will eventually be able to measure the positions of those gaps to 1,000th of one of those pixels that you can see. So we're very excited about this, but we still have a lot of work to do. NEID will begin producing science this year. We're working very hard. The whole team is working very hard. Well, I'm not. I'm talking to you. But everyone else is working very hard to get the instrument stable and producing the precise radial velocities that we now know that it will be able to produce. We have a lot of very strict operational requirements to meet on the telescope guiding, the telescope focus. There are all sorts of corrections that the interface between the instrument and the telescope have to meet. This image on the left, this beautiful image, is one of the calibration images that we take to demonstrate that we're meeting those requirements for that unprecedented radial velocity precision. The symmetry that you're seeing there, those lines are caused by a series of prisms or gratings, and the symmetry proves the telescope is doing its job extremely well and making all of the corrections that we want. When we feel that we're meeting all of the requirements, we will then undergo our operational readiness review by NASA, and formal science operations will begin. Until then, science will be happening on what we call a shared risk basis. That is, we're going to practice and improve the instrument on real targets, doing science that the community has proposed, but on a shared risk basis because we're not sure we're quite at 30 centimeters a second where we need to be. So we're very excited about this milestone in NEWID's development, very excited that science is going to be happening very soon, very excited about all the work we have to do because we finally have first light with NEWID. Thanks.
Thank you for coming here this warming up. Wanted to thank the friends of mine and my students in the first row here from Villanova University who are attending. This paper was done called Living with a Goldilocks Star. We think we're making the case that these may be the best stars for hosting habitable planets. My colleague Scott Engel will stand up, and Casey Purcell, just stand up. No one's going to see your back. They're not allowed up here. There you go. Thank you. So what we'll be talking about is making a case that these stars may be the best stars for, or Goldilocks stars for hosting planets. Let's see, pressing the down button, I guess maybe there. Okay, we had started this kind of program over 30 years ago called The Sun in Time, where we studied solar stars and their capability for hosting planets. And because what happens is that the X-ray and UV radiation of stars, especially G, K, and M stars, has a major effect on the atmosphere and water inventories of hosted habitable zone planets. So what this deals with, you see there, is what we deal with is number 2, the effects of solar and stellar X-ray radiation and UV radiation winds. Those do a number on a hosted planet. A number meaning it can throw away or blow away the atmosphere and destroy the water content. So that's going on. Then we decided to do what? Where do you see the arrow? Arrow now? Okay. This is a, I did that one. We also did red dwarfs. We skipped over K-stars, but we wanted to do something extreme. And red dwarfs are the most common stars in the galaxy, so we took on them and had a program starting about 15 years ago where we studied collected our own X-ray, UV observations, and did photometry. We called those Living with a Red Dwarf. It seems like you have a higher probability of getting funding if you give a project a name. So that's why you see names for most of these. And this program is still continuing. And next is to show you what K-stars are. This is the Alpha Centauri system, which shows Alpha Centauri A, which is over there, the bigger one, which is a little bit more massive than the Sun and older. And then the Sun is in there for comparison. Alpha Centauri B is a K-star, so this is the objects we're studying. It's the nearest one. And then you see Proxima Centauri, for comparison, as an M5 star. So there's a big difference in sizes and things of that sort. So the M stars have masses of 60 to 80% or so of the Sun. Their temperature is a little bit lower, 4,000 to 35 to 5,300. And luminosities are less, approximately half or less than half the Sun. But what is important here is their lifetimes. Solar stars have lifetimes of 10 billion years, which seems like a long time. These stars have lifetimes of 15 to 50 billion years, which is going to play a role in why we selected them as Goldilocks stars. This gives you a plot of histograms showing that G stars, K stars, and M stars. The M stars are predominantly the most common stars, 73%. K-stars are of the order of 13% or so. G-stars are rather rare stars. We think they're not, but a G dwarf is like 4 to 5% of total stars in our galaxy. So they're not very common. They're rather rare. This plays a role too. Second, this shows evolution of different types of stars. F stars only last a few billion years. G stars have a lifetime of 10 billion, and they change. The sun, for example, changes 6 to 7% per billion years. So 4.5 billion years ago, the sun was 70% of what it is today, which led to problems with the cool star or dim star paradox, how we didn't freeze over. It was solved because of greenhouse gases. But the sun is increasingly getting luminous, which is getting close to, the Earth is getting close to the inner edge of the so-called habitable zone. In a billion or so years, it is no longer in the habitable zone of the sun, which causes problems. You see K-stars evolve much slower. In 10 billion years, which is the total lifetime of the sun, where it becomes a red giant, a K-star changes 20%. So it still has a lot. It's changed, but not much. And so planets orbiting that wouldn't feel very much or wouldn't see climate changes. M-stars don't change at all, and they last to hundreds of billions to a trillion years. These are our results, which I'll skip over real fast because this is the science part. We do rotation versus age. So what you see plotted is rotation in days and age at the bottom. Stars spin down with time. They lose angular momentum through their magnetic winds. Young stars spin fast. Older stars spin down and lose angular momentum. And G-stars and K-stars and M-stars all do this. We use this as a way of getting, called geochronology. We use this as a way of getting ages. K-stars evolve so slowly that evolutionary tracks and isochrones don't work. So we've calibrated these stars as members of clusters and moving groups, in some cases binary stars, to get their ages. So if we find a K-star with a planet, if we know the rotation, we can, like say it's 35 days, we can give it the age. That would be like 4.6, 4.7 billion years. So it's useful in planetary work. This diagram is a bit busy, but it's showing you that as time goes on, when stars are spinning fast, they have strong dynamos. Strong dynamos means magnetic activity. So young stars have strong X-ray activity, strong UV activity. In case of the K-stars and the G-stars, 1,000 times stronger than, for example, what the sun has present. And the UV radiation, which we use Lyman alpha as a proxy for, we're looking at 6 or 7 times stronger. So young stars are really on fire and with flares and activity. And it's a problem for the planet to endure these X-ray and UV radiations. Also winds. Winds are higher in younger stars. It's hard to figure out exactly higher, but in terms of K-stars, it looks like they're of the order of 30 to 40 times higher. Winds play a major role too, and we'll see this in the next slide. So why we do this X-ray and UV radiation and wind is because X-rays, I'll just do UV first, FUV radiation, far ultraviolet radiation, produces photodissociation. I'll give an example there, water, H2O. Broken up into hydrogen atom and an oxygen. X-ray radiation ionizes. It strips the electrons away from these atoms. So you get a proton and you get an oxygen missing 1 or 2 electrons. This is what's happening in our own ionosphere. It has hydrogen ions, oxygen ions that came about from the dissociation of water. Solar wind is a plasma with charged particles, electrons, protons, and so on. The trick that happens is if a planet does not have a magnetic field, these ions that are exposed and put out on the ionosphere are swept away by the wind. If no magnetic field, look at the bottom line there. This is from Lammer et al. The bottom line says, no geomagnetic field, no water, no life. It's probably true. In our own solar system, we have 2 or 3 terrestrial planets in the habitable zone. The only one that's habitable is us. We have a strong magnetic field. We always did. Mars once had one. It lost it 3.5 billion years ago. It had oceans. It lost it. The sun then started to erode the atmosphere of the planet away. Venus never had a chance. It lost its water supplies very, very fast. And then what you have there is just volcanoes producing CO2. Without a magnetic field, this means no atmosphere and probably no life. This shows you the magnetic field effects, is that the Earth has this magnetic field that it doesn't protect you from the X and UV radiation because it doesn't care about the magnetic field. It penetrates it. It's the winds that are deflected. Most of them are deflected around, and they don't reach down to grab off or to skim off some of the ions. Well, it actually does. Earth is losing a tiny fraction of its atmosphere, but without a magnetic field, it would have lost all of it. This is our plot showing that why we go back to K-stars. There's nothing wrong with the G-star, just that they don't live as long. They're perfectly fine, as we see. The Earth is here. Maybe Mars could have had life once. Maybe does now. But what happens is that K-stars do get slightly, because you have to be nearer to them, they do have higher levels of X-ray and UV radiation, 10 times, 20 times higher than Earth. When you get into M stars, you see the M star there, M1. You get into Proxima Centauri, M5. You get into M8, you see TRAPPIST. You're getting, let's look at Proxima Centauri. You're getting 500, 600 times more X-rays on that planet now. And if you go back in time and go back when Proxima was young, Proxima's 5 billion years old, you extrapolate back using our graphs, it was getting 100 to 200 times more X-ray radiation. We have, even though I worked on the Proxima Centauri project, I'm somewhat concerned that that planet has any atmosphere left and water left for life to evolve. We gave the odds as 15%. That it could have lost its atmosphere and maybe be resupplied by comets and things like that, falling in after the star slope. Look at TRAPPIST, which is a fantastic star system. You see these planets are all lined up, but they're orbiting an M8 star, and the habitable zone number there is 0.02, 2 million miles from the star. They are getting really bombed with X-ray and UV radiation. The number we give is 1,600 X-rays. So that's being conservative. When that star was younger, it was higher. So we have some concerns about whether the planets there are really suitable for life. We'll find out soon, I hope, when we start to take images, because they do transit. This is a summary. You see the M stars with their tiny habitable zones. If you want to be warm, you have to get close to the star, but you're getting close to a nuclear power plant with X-rays and UV radiation. So if you want to be warm, you get close to that star, but then that star is emitting huge amounts of X-rays and UV radiation. And you have K stars in the middle, which is why we have them as Goldilocks stars. Then we have the M stars, where the habitable zones go from 0.95 to about 2 AU. And that gives the percentages. This gives some examples. We took some familiar examples out, the Sun, Earth. The lifetime of the Sun is about 10 billion years, but our lifetime, as with Earth, is about 1 billion years before the Sun gets luminous enough to cause a runaway greenhouse effect, unless we speed it up. I mean, it could happen in 500 years if we speed it up with greenhouse gases. And then we have what's called that Kepler 442 is called the Goldilocks star, because it's almost like the Sun, almost like the Earth. Same sort of similar size, mass, and the amount of radiation it's receiving. It gets about 50 times. We think that 50 times might be tolerable if that planet has a magnetic field. We have Proxima listed. Then the bottom you see TRAPPIST, which is getting huge amounts of radiation. We have a little caution zones there for Proxima Centauri and TRAPPIST, where the X-ray radiation is hazardous. You know, they could have extremophiles. We have things that live, tardigrades and things like that live in nuclear power plants, and they might be quite happy on planets like that. Radiodorans, these microbes that love X-ray radiation. But we don't. So here's the conclusions. It's hard to argue with success. The Sun, has a planet. that has complex life. It's the only one known so far. So, but the problem is, how much longer will have complex life? And if you just throw in the sun evolving 7% per billion years, in somewhere in the order of 1 to 2 billion years, it might be closer to 1, a greenhouse, the Earth gets warmer, a greenhouse effect ensues, it's a runaway greenhouse, which causes the CO2 to come out of the oceans and warm the Earth up a lot. So the Earth starts to lose its oceans, and in about 2 billion years, it becomes uninhabitable to most like us. Although tardigrades and things like that might be happy there. In terms of studying life, the sun is a rare. Solar stars are rare stars. So if you're looking for life, M stars are fabulous because you have so many of them. G stars aren't. They're 4 or 5% of all stars. So that's another thing. You would love the M stars to be, and they still could be, good stars for habitable planets and life. We don't know. It will depend on whether they have strong magnetic fields, the planets hosting them. Case for the K stars is that they're between this is the Goldilocks syndrome. They're between the shorter-lived, more luminous G stars and the long-lived, very, very magnetically active M stars. And so we call the K stars Goldilocks stars because they seem to have the properties that are conducive, the properties of the solar stars, which don't have too much X-ray and UV radiation compared to the M stars that have huge amounts. The K stars have long lifetimes, 15 to 40 to 50 billion years, which gives you a long time for life to evolve and to advance. There are several K stars that are really old. There are no really old G stars because they die out at 10 billion years. They're white dwarfs now. And there are 2 or 3 times, if you're looking for planets, you're not getting like 75% of all stars. You're getting 2 or 3 times more of them, K stars, than M stars. And finally, there is this concern that people are starting to have with M stars in that they, being so close to them and being so magnetically active, they are and flares. They are enduring fairly large amounts, not fairly large, very large amounts of X-ray, UV, and winds in addition to the flares. So it might be problematic that we don't care. It's not the life. It's whether the atmosphere, it's whether the planet has an atmosphere and water for life. And that's what we're concerned about. This is Goldilocks making, schematic Goldilocks, making her decision on the warmer, the perfect middle bowl of porridge, which was just right. Thank you very much.
Thank you to our speakers. We'll now be taking questions from the room. Before you ask your question, please state your name and affiliation and wait for the mic. And if you are watching the live stream, please queue up your questions in the chat and Rick will convey them to us. Technical difficulties.
Hi, this is Ethan Siegel from Starts with a Bang. This question is for Daniel Gilman. As far as I know, the best constraints that I quantitatively know of on the mass of a thermal relic particle candidate for dark matter comes from the Lyman alpha forest, and that those constraints give you an equivalent rest mass if you've got a thermal relic of somewhere in the ballpark of 5 to 10 keV per particle. What quantitative constraint on mass does your study put on the mass of a thermal relic equivalent? How does it compare to Lyman alpha constraints, or alternatively, any better constraints that I may not know about?
Thanks for the question. Oh, not on. Is that good? Is it on? All right, cool. Thanks for the question. It's a great question. So the result that we got in terms of KeV, so this is a mass of a dark matter particle, and it was 5.2 keV. So we said that whatever dark matter is, if it is a thermal relic, it has to be more massive than 5.2 keV. The result you quote from the Lyman alpha forest, I believe the latest measurement is 5.3 keV. There was a recent paper from Stellar Streams, and I think they quoted 6 keV. I don't remember off the top of my head. But what's important is that each one of these techniques is completely independent. They have different systematics, and they ultimately are measuring different things. So the Lyman alpha, they measure different things and arrive at the same conclusion. So for instance, Lyman alpha, what they're measuring is something called the flux power spectrum at very high redshift. So they basically map the power spectrum of density fluctuations at high redshift, and they use this to infer a dark matter particle mass. We measure the halo mass function directly, which is just the number of halos per unit mass. And so these are two different ways at getting the same information, which is how much structure is there as a function of scale, or how much structure is there as a function of mass. And so what's important is that these are two independent techniques, and they complement each other in that way.
Hi, Adam Mann, freelance also working for Life Science. My question is for Geoff. You said this is potentially a crisis, and I guess I'm just wondering, what personally you think is the resolution? Do you think it's new physics, or do you think it's more systematics?
Every time when I sleep, I always worry that this kind of systematics will affect our results. So, for example, that's why independent measurement is really important, because we don't really know whether the measurement is real or not. So one of the slides I have been shown is that the Freeman, they use a different calibration method to calibrate the supernova. So the reason they want to do it is because they really worry that what the Shields team used as Cepheid, one of the methods to calibrate the supernova, will cause the higher value is caused by some unknown systematics. So the unknown unknowns is really hard to reveal by using only single method. So, but after our result comes out, I personally feel that this crisis is more like a real. So now, before our result comes out, actually, I think a lot of people question the supernova measurement. So there are a lot of people say that, oh, maybe you can, there's a mystery force affect the supernova result. But after our result comes out, a lot of scientists start to believe that the tension is real. So you can see in the archive, a lot of papers shows up and say, how do we resolve this tension? So I think in generally, the cosmological community is moving toward to believe that the tension is real. Thanks.
Govert Schilling, freelance from the Netherlands. Question for Daniel Gilman. Could you try to explain why the brightness of these multiple image quasars is so strongly dependent on the size and the number of the subhalos?
Yes. Let's see. So the brightness depends on fluctuations of second derivatives of the projected gravitational potential near an image. I'm not sure if there's a way to phrase this in simpler ways, but essentially, if you put a very small structure nearby an image, then the total potential or the total effect on the mass doesn't change. Well, let me see how I can say this. Essentially, the images are probing very, very small fluctuations in the local mass density. And so they're not as sensitive to the overall smooth distribution and its profile, but what they probe are very small deviations around a smooth profile near an image. And so if you have something like a galaxy that's very massive, it varies on relatively large scales compared to these halos. As you start to throw in these halos, you produce these small fluctuations that will then have a relatively large effect on the brightness and less an effect on where the images actually show up. Anna, do you have a better way of saying this?
The second derivative is the change of the slope. So if you just do the math.
Want to hit the mic?
Sorry, just The second derivative is like the change of the slope of the mass distribution. So it just mathematically, if you work out gravitational lensing, like Daniel said. So the brightness is the second derivative, which is the change in the slope. So you just need a small thing to change the slope. You need a much smaller thing to change the slope than you need to make a change in like the overall mass.
This question's also for Daniel, sorry. Pamela Gay, Daily Space Astronomy Cast. You said at the beginning of your presentation that galaxies appear to have halos, but dark matter halos, but there's been some recent discoveries that appear to show galaxies that are lacking dark matter. Does cold dark matter models help explain the existence of some of these rogue dark matterless systems?
So the systems that you referred to are truly new and just very weird things. I'm not sure if cold dark matter helps explain them. I mean, this is the kind of thing that you have to explain in the context of cold dark matter. So yeah, I'm not sure.
Wade Gibbs for Scientific American and IEEE Spectrum. A question for Jason. You said you need 10 centimeters a second precision to detect Earth-like planets around sun-like stars. What does 30 centimeters per second, which is what you're doing with NEID, actually get you?
Sure. So what I said was that an Earth-like planet or a sun-like star in the habitable zone is 10 centimeters a second. If you go to, for instance, K dwarfs, then the amplitude is higher in the habitable zone, even for an Earth-mass planet. So 10 centimeters a second is a wonderful benchmark. It's a wonderful target for all of us to aim for, but there are terrestrial habitable zone planets that are detectable at 30 centimeters a second. The second point is that I don't want to conflate how precise the instrument can measure a star's velocity with the amplitude of the planet it can detect. If I make many hundreds of measurements, even if an individual measurement is only precise at 30 centimeters a second, I can still detect an amplitude of 10 centimeters a second because I have a lot of data to do it. Just in the same way that even though my pixels are 1,000 times too big to make this measurement, if I have enough of those pixels and enough data on them, I can centroid things to 1,000th of a pixel. The final point is that the instrument is only one source of noise in the detection of these planets. The stars themselves, their atmospheres are moving around at kilometers per second. And so you have all of the gas on the surface going up and down at 100,000 times faster than the things that we're looking for. And so we need all of those to average out. And they average out very well, but they average out to about 1 meter per second. So to get those last 2 orders of magnitude and come down, first we need to measure the residual stuff as well as we can, and that's why we need the 30 centimeters a second. But then there's also a large effort in the whole astrophysical or exoplanetary and stellar astrophysics community to understand how we can diagnose those last few bits of residual motion that we're still detecting and distinguish it from the motion of the planet. And there are a lot of tricks we can play with wavelengths and which lines we choose and how the line shapes change. It's a big ongoing effort in the whole community.
One follow-up question. Have you selected your first target for real science when you commission the instrument?
Oh, I mean, we will do real science with okay, so yes, I'll say yes. Our team is just one team doing a lot of science with NEID, and so the instrument team has been awarded some guaranteed time with the spectrograph, sort of as part of the exchange of we built it and had the contract, but we also get some use on it for a few years to look at whatever we like. And so we've chosen to look at G and K stars, some of the very brightest ones in the sky, the closest ones to Earth. And basically, we want to take NEID out for a spin and see what it can do. These stars have been observed for decades. So the very first planet searches were looking at these stars. But for the first time, we think we can access the terrestrial planets in their habitable zones. And so we're going to spend the lion's share of our time getting hundreds of measurements of these and seeing the planets that everyone else has missed so far.
Since we're about out of time, Rick, do we have any questions from the chat?
Well, we did, but they actually were already answered.
Oh, brilliant. All right, I'd like to thank our speakers again, and thank you to everyone for being here. The next press briefing will be at 2:15 this afternoon, where the speakers will be discussing satellite constellations and their impact on astronomy. Thanks.